Welcome to ICU Primary Prepcast. Hi, my name is Swapnil, and I'm joined by my co-host, Dr. Mike Clifford from Melbourne. Hi, Mike.
Hey, Swapnil, how are you?
I'm good. How are you? How's the weather in Melbourne?
It's pouring with rain and about 12 degrees, which is how I love it.
Yeah, very similar in Sydney today. So let's dive into today's snippet. And the question is about the carriage of carbon dioxide in the blood. So how will you tackle that?
Okay. So this is a pretty bog standard question, Swapnil. It's the brother or sister of O2 carriage, which people are very good at. And then when you ask them about CO2, they all seem to go a bit blank. And there's a couple of reasons for that. One is that one of our chief references is very confusing. So a lot of the answers are fundamentally flawed from the beginning, and I'll go into that. But if we think about it, there's a graph of O2. The oxygen dissociation curve has a curve which, if you convert it to content, gives you about 15 to 20 mils of oxygen. Now, CO2 is double that. Okay, it's up closer to 50 mils. So if you go to CAM, you'll see a CO2 carriage curve, and that's the one to learn. And it tells you that arterial blood contains about 48 mils of CO2 for every 100 mils, and venous blood contains about 52 mils per 100 mils. So the difference between arterial and venous is 4 mils of CO2 per 100 mils, which is 4 mils per litre, which is 200 mils per 5 litres or cardiac output. And if you remember that we consume 250 mils of oxygen, we produce 200 mils of CO2, and there's your VQ of 0.8. So that works, right? So there's a few little key numbers to remember. Now, here's where it gets a little bit complicated. The amount of CO2 in the blood is 5% dissolved, 90% bicarbonate, and 5% carbamino compounds. Okay? Now, if you look at the graph in West, it has two columns. One is the column of arterial content, and the other is the AV difference. And unfortunately, it shows those two columns to be the same height. And it gives numbers of 10%, 60%, and 30% in the AV difference box. But bizarrely, he made that column height the same. So everyone confuses the AV difference with the venous content, okay? But the venous content is very, very similar to the arterial content. It's 6% dissolved. It's about 86% bicarbonate and about 10% carbamino. So the differences are very similar. But those 10%, 60%, 30% numbers refer to the AV difference. And it's important that people recognise that that's not the venous content. Right, so we get rid of that confusion. So CO2 is very soluble. So a lot of it is dissolved in blood, much more soluble than oxygen. Bicarbonate, we know that there is a reaction with CO2 and water to produce hydrogen carbonic acid, which then dissolves into hydrogen and bicarbonate. And the first step of that is very slow, but it's actually expedited by red blood cell carbonic anhydrase. So CO2 dissolves into the red cell, combines with the water, gets converted to hydrogen ion and bicarbonate, and the hydrogen gets trapped inside the red cell, but the bicarbonate diffuses out in exchange for chloride. So your chloride goes down, and that's the hamburger shift, okay? And that's why red cells are slightly bigger in the venous blood than they are in the arterial blood. So your hematocrit of venous blood is slightly different to your arterial blood because the red cells are slightly swollen, okay? The last component is your carbamino compounds, and that's where CO2 reacts to available amino groups, particularly on hemoglobin to perform carbaminohemoglobin, and to a lesser extent with amino groups on other plasma proteins, particularly albumin, which is why albumin is considered one of the buffer proteins because it's binding with that CO2, okay? And the classic group is the imidazole group of the amino acid histidine, which provides significant buffering. And this is where our Haldane effect comes from. And that reflects the difference in CO2's ability to bind to oxygenated versus deoxygenated blood, okay? And that effect is partly due to the ability of deoxyhemoglobin to buffer the hydrogen ions, okay? Because reduced hemoglobin has about 3.5 times the affinity of carbon dioxide than oxyhemoglobin. And that's why you'll see when you look at the little graph of content of CO2 in venous and arterial blood, there's a jump up step, okay? So you would expect it to be tracking along one line, but like an electron in a shell, it leaps up. And that leaping up is a function of the Haldane effect. For each CO2 molecule that we add to red cells, the osmotic pressure is increased, okay? And that's why they change their size. So that's it. That's basically it. And the 4 mils of extra CO2 that's contained in the venous blood is the CO2 that's eluted through the lungs in your exchange. So it's dissolved much more efficiently than oxygen in the blood. There's an enormous amount that's carried by bicarbonate, by far and away the predominant fraction. And there's a small amount that's bound to the histidine molecules. And that percentage increases between arterial and venous blood proportionally because of the Haldane effect. And that's it. That's CO2 carriage.
Thanks, Mike. As you mentioned, this question can be a bit confusing. And a lot of candidates ask me this question because they always get confused. Should I write about partial pressure of arterial CO2 versus enteral CO2 difference, why it exists, and then talking about dead space and all those things? Is that really necessary for this question?
No.
What's your thoughts and why? Why is that?
You can remember the partial pressures because they're relatively easy, 40 to 45 and then 45 to 50 in venous blood. But it's easier to think of content, 48 mils and 52 mils, because that is what's actually traveling around the bloodstream in the 3 different forms. So the CO2 as bicarbonate or as a carbamino compound doesn't contribute to the partial pressure. So that's why even though the partial pressures are relatively small changes, the content is significantly more. And that's because of all of these 2 other forms of CO2. So you're better off thinking about content, I think. Dead space and ventilation and all those other things is not relevant to this question. So you're purely to contain yourself to where is the CO2 in arterial, where is it in venous, what's the difference? And it's important not to get confused by that absolutely terrible graph in West. So I'll send you a graph for the show notes, Swapnil, but people should go out and find the graph of the arterial content of CO2, the venous content of CO2, and the content of the arteriovenous difference, which is only 4 mils, not 48 or 52 mils.
Thanks, Mike. I think that's very useful. And that clarification, especially from the West, is really important. So that's the end of our today's snippet. We'll be back with another snippet in a week's time. Till then, goodbye and have a nice time.
See you later. Good luck.